In today's video, we'll be talking about work and energy and the relationship that the two share. So after watching this video, you should be able to understand what a conservative and non-conservative force is, understand how mechanical energy can be changed in terms of its form, and then be able to apply the work-energy relationship to solve various problems that I might present to you. So we got a lot of stuff to cover. Let's get right to it. Back probably a few months ago, we had said that all the different types of forces that exist can be categorized basically as contact forces or action at a distance forces. And basically a contact force was one that was directly touching you, and then action at distance forces were ones that didn't have to be in direct contact with an object, such as gravity. In this lesson, we're going to basically talk about how we categorize forces basically on their ability to change the total mechanical energy of an object, okay? And whether or not it's able to do that. Not all forces are, but that's what we're talking about, is what is their ability to change the total mechanical energy on an object. And the two categories of forces are referred to as conservative and non-conservative forces. So that's kind of, we're just kind of sort of switching things around from contact and action at a distance forces to conservative and non-conservative forces. But before we do that, I kind of like to talk about, well, what the heck is mechanical energy? Okay. Mechanical energy basically refers to the amount of potential and or kinetic energy that an object has. Just for instance, if you say you have like a roller coaster track and it looks something like this, okay, and a car is right here and it's flying down the track. This car at this moment in time has kinetic energy because it is moving, right? And it also has potential energy. And why does it have potential energy? Because it's above the ground. So an object can have both kinetic and potential energy at the same time. But if you add those two numbers up, those values up, that equals the total mechanical energy that that object has at that point in time. So let's start to break down what a conservative force is. Okay. A conservative force is a type of force that is able to have potential energy. Okay. If you can calculate a potential energy for that force, it is a conservative force. Their work path is independent, okay? And basically what that means, I'll get to in just a second. Let me tell you what the conservative forces are. The conservative forces are only gravity, which another way of saying that is the weight, the force of the weight, and the spring force, the force supplied by a spring. In particular, we're probably going to focus more on the weight force than the spring force for most of these problems. I don't want to say all of them, but for most of them, it'll probably be weight. And what does it mean that the work path is independent? Well, basically what that means is if this is the ground here, okay, and let's say I want to lift a ball up that's just right here, and I want to get it to this point up here. I'm going to lift it to, I don't know, 5 meters up. Okay, let's say this is 5 meters up. If I lift this ball up and I go just straight up 5 meters, okay, I've increased its potential energy. Okay, we could calculate that with the formula for potential energy. I also could take this ball and I could whirl it around, I could twirl it and do all this stuff with it, and then still place it up about 5 meters. Is the potential energy different in that ball if I just lift it straight up, or if I do all this whirling and twirling? And the answer is no. There is no difference in the amount of potential energy that ball has, because the potential energy is based upon the height of the object above the ground, basically. So the work path is independent. It doesn't matter how it gets there as long as it's there, okay? And that's what's meant by that. It's just probably a fancy way of saying something that probably could be said easier, but that's the way I said it. All right? Now, work done by conservative forces does not change the total mechanical energy of the system. Okay, it doesn't change it. When there are only conservative forces, the total mechanical energy is conserved. Okay, and so what we're going to find out basically is that conservative forces are able to basically switch between kinetic and potential energy, but if you add the kinetic and potential energy up as a whole, it's going to be the same always. Okay, the mechanical energy is conserved. It does not change. Okay, so basically the force of gravity, or the weight force, and the spring force are conservative forces, and they are not able to change the total mechanical energy of a system. That's basically what that's saying. All right. Now, what about non-conservative forces? Okay, non-conservative forces. This is where things start to get a little bit more interesting. Non-conservative forces, you are not able to calculate a potential energy for them. Okay, their work path is dependent. Okay, because what a non-conservative force is, basically the formula for work is force times distance times the cosine of theta. Okay, so their work path is dependent. So it's important to figure out the displacement of this object. The non-conservative forces are the normal force, the force of friction, the force of air resistance if you have a tension force in like a rope or a wire, and a applied force, so if you like push something or hit something or whatever the case may be. Basically, my trick to remembering this is if it's not the force of gravity or the weight force, and if it's not the spring force, then it's a non-conservative force. If you can kind of keep that in mind for this part of the semester, you'll be peachy, okay? Because basically those are the only two forces that are conservative is the weight force and the spring force. So non-conservative force is basically everything else, okay? So what happens if work is done by a non-conservative force? So what happens to the mechanical energy of an object? Well, the answer is work done by a non-conservative force does change the total mechanical energy of a system. Okay, so basically if a non-conservative force acts upon an object, it can change the kinetic energy, the potential energy, or both. And basically it can either increase or decrease the total mechanical energy of the system. So when net work is done by a non-conservative force, the mechanical energy is not conserved at that time. Okay, it is not conserved. So this is kind of either adding or subtracting energy from the system by introducing this non-conservative force. Okay, so why do we care about non-conservative forces? Well, when work is done upon an object by an external force, such as like an applied force or the force of friction or whatever the case may be, the total mechanical energy, the kinetic and potential energy together, is changed. Okay, it's changed or altered in some way. The work that is done will be equal to the change in the mechanical energy of that object. Okay, so you just use your work formula to figure out how many joules of work is either added or subtracted to the system. The gain or loss in energy can then be turned into basically in the form of potential or kinetic, or both, potential or kinetic energy for that system. Okay, and if you're feeling thoroughly confused at this point, don't worry. Once you start to get to some examples, this won't be so bad. But right now I'm just kind of laying the foundation, so just get these things down in your notes, and then things will start to make a little bit more sense in a bit. Okay. Now, what about conservative forces? Okay, conservative forces, remember, is the weight force and the spring force. When the only type of force doing work upon an object is a conservative force, the total mechanical energy is conserved, or it stays the same. Okay, so if you add up the amount of kinetic and potential energy, and it will add up to the total mechanical energy of that system, and that will remain the same, remain constant. Now, can kinetic energy be changed to potential energy and potential energy changed to kinetic energy? Absolutely. I mean, that goes back to this roller coaster idea, where basically here's this roller coaster. This car up here has a lot of potential energy and not much kinetic energy. It's probably pretty slow moving at the top of this hill. But down here in the bottom of the hill, it has a ton of kinetic energy and very little potential energy, so that it's shifting. And the only force acting upon this roller coaster, assuming it's friction-free, will be the force of gravity. Okay, and so that is a conservative force, and basically, if you add up all the kinetic and potential energy at any point in that system, it should remain unchanged throughout the entire roller coaster ride. Okay, let's do some examples to maybe kind of help clarify what is going on here. So it says a baseball is traveling upwards towards a man in the bleachers. So someone just hit a baseball and is traveling upwards to the man in the bleachers. I guess it's a home run. That's great. I want to know, is this an example of going from kinetic to potential energy? And let me back up before I say that. All these examples are solely conservative forces in action. Okay, these are all conservative forces. I'm going to do nothing with non-conservative forces at this time. So these are all conservative force examples. So a baseball is traveling upwards towards a man in the bleachers. Okay, so this ball was hit and it's going up into the air. So it's moving and it's increasing its height. And so this would be an example of kinetic energy going towards potential energy. Okay, it's going to be way up in the stands in the nosebleed section. Okay, so that kinetic energy is being converted into potential energy. This second one's kind of tricky. A bungee cord exerts an upward force upon a falling bungee jumper. Okay, so this bungee jumper is falling downwards. Okay, and the cord is pulling up on this bungee jumper. Okay, so he's traveling really, really fast and he's slowing down because of this cord being stretched and basically slowing him down. Okay, and so this would be an example of kinetic energy to potential energy because he's slowing down and he's going to start to be actually sprung back up. A bungee cord is kind of an example of a spring. If you stretch a spring out really, really far, all of a sudden you kind of like stop at this point and then you get snapped back. That's basically what's going to happen to this guy. He's still falling downwards, but he's slowing down and then eventually he's going to like reach that maximum stretch point and then he snaps back up to the, I don't know, the bridge or whatever it is he jumped off of. The spring of a dart gun exerts a force on a dart as it is launched from its initial rest position. So basically the spring's all coiled up and there's like, I'm not a good drawer, but there's a dart and basically the spring expands and pushes this dart out. And it started at rest and now it's flying out. So this would be an example of potential energy to kinetic energy. Okay, so these are all examples of basically conservative forces in action. The point to these examples is, though, if you add up all the kinetic energy and all the potential energy, whatever the initial, KE initial plus potential energy initial, must equal the kinetic energy final plus the potential energy final. Okay, it's conserved. All of the energy is conserved in these systems. Before we start talking about non-conservative forces, I just want to make something relatively clear here. You can have negative work. I mean, we've seen positive work in action, but you can actually have negative work. And you may say, well, how does that occur? Well, first, let's talk about how you could have positive work, which is this first example. If the force and the displacement are in the same direction, positive work is done on the object. And basically, when you have positive work done by a non-conservative force, it gains mechanical energy. And so an example of this would be like if you were to, push someone. Here's someone that's getting pushed. The force and the displacement are in the same direction, and so you've put positive work on this person that you just pushed. Okay. Now, how can you have negative work? Basically, negative work is if the force and the displacement are in opposite directions, negative work is done on the object, and the object loses mechanical energy. An example of this would be like a car. I'm not a good drawer, but here's a car and it's moving this direction and it applies its brakes. And so the force of friction is going to oppose the motion of this car. And so the force is this direction, it's moving this direction, the displacement's to the right, the force is to the left, and so you'd have negative work being done on this car. All right, and so that'd be an example of negative work. So is there a nice, easy formula for relating work to energy? There is, and this might help, again, clarify what's been talked about thus far. The initial kinetic energy plus the initial potential energy plus any work that is added from non-conservative forces will equal the final kinetic energy plus the final potential energy. And just a reminder, work by non-conservative forces can be positive or negative. So this term right here, this value can be positive or negative. You have to just figure out, is the force and the displacement in the same direction or are they in opposite directions? And that's going to determine whether or not that term is positive or negative. And this work energy relationship that's going on here is really useful actually for solving some problems, which we'll see very shortly. But keep this formula in mind because I'm going to use it in some example problems coming up. So here are some just statements, and I'm wondering, was positive or negative work done, and did the object gain or lose potential / kinetic energy? Okay, so positive or negative work, and did it gain or lose potential / kinetic energy? So there's a lot of options we can write for each of these things, but we'll go through it. A weightlifter applies a force to a barbell above his head at a constant speed. Okay, a weightlifter applies a force to a barbell above his head at a constant speed. Okay, so basically, here's this little barbell. It's moving upwards at a constant speed. Was positive or negative work done? Well, to move this barbell up, the force must be up, and the displacement is also up. So this must be positive work was being done. Now, did this barbell gain or lose potential energy? Well, it gained potential energy. Why? Well, basically because it's now higher above the ground. Okay, the higher you are above the ground, the more potential energy you have. There was no change actually in the kinetic energy, and the reason why is because it was moved at a constant speed. Now, if this barbell all of a sudden accelerated or started moving faster, then there would be a gain in kinetic energy, yes. But for right now, there's really no change in the kinetic energy. It's just stagnant. But there was a gain, or there was positive work, and there was a gain in the potential energy. Let's do another one. The frictional force between the highway and a car tire pushes backwards on a skidding car. Okay, so again, here's this car. It's moving this direction, so this is the direction of the displacement, and the frictional force is in the opposite direction. So this is an example of negative work. Negative work. Did it gain or lose potential energy? Well, the question you need to ask yourself is, did the car raise itself or lower itself above the ground? And the answer is it didn't really change its position relative to the ground at all, right? So the potential energy, there's been no change. Has the kinetic energy changed? Yes, it has. It lost kinetic energy. Okay, how did it lose kinetic energy? It's slowing down, right? The frictional force is causing the car to slow down. Let's take a look at a third example. A t-ball player hits a long ball off the tee. During the contact time between the bat and the ball, the bat is moving at a 10-degree angle to the horizontal. Okay, so here's this like t-ball, and it's shot at a 10-degree angle above the horizontal. Okay, so the force and the displacement are in the same direction. So this is an example of positive work. Did it gain or lose kinetic energy, or was there no change? Well, because the ball is stationary, now it's hit off the t-ball, it gained kinetic energy. And the tricky part might be to realize that this t-ball is now higher above the ground than it was before, because it wasn't just shot horizontally off the t-ball. It wasn't just like a line drive. It was shot at an angle 10 degrees above the horizontal. So it's actually going to gain potential energy too. Okay, because it's getting higher, all right? So these are some examples of basically just looking at did it have positive or negative work, and did it gain or lose potential and or kinetic energy? Okay. Due to the length of this video, I've made a second video with solving two example problems using the work-energy relationship formula that I mentioned in the previous slide. So if you want to check that out, hit up the website and you can see me work two example problems. But just in the essence of time and trying to keep these videos under 20 minutes, I'm going to stop here. So that takes care of this video. I will see you guys next time.